Right now, something strange is hurtling past our sun. We don't know exactly what it is or where it came from, but it's shaping up to be one of the most bizarre and fascinating visitors our solar system has ever seen. So, what is this thing? What is this cosmic mystery that has the entire astronomical community buzzing? Well, for starters, it's an ancient traveler from the void between the stars. It's named 3I/Atlas, and get this, some estimates put its age at over 7.6 billion years. That would make it nearly twice as old as Earth itself. But here's the crazy part. Just as it's making its closest, most active approach to our sun, we can't see it at all. The sun's glare is completely blocking our telescopes, shrouding this mysterious visitor in even more secrecy. So how did we even find this thing? Well, the first clue that 3I/Atlas was something really special wasn't its size or its shape, it was its incredible speed. When it was first spotted back on July 1st, 2025, astronomers were just floored by how fast it was going. I mean, think about it. We're zipping around the sun at about 30 kilometers per second. Mercury, which is way closer, has to book it at 48 kilometers per second just to stay in orbit. And this new object, way out near Jupiter, it was already blazing past at a mind-boggling 58 kilometers per second. Yeah, that incredible speed, that's what we call escape velocity. It basically means our sun's gravity just isn't strong enough to grab onto it. It's on what astronomers call a hyperbolic trajectory, which is, a fancy way of saying it's on a one-way slingshot ride through our solar system. It came from deep space, and it's headed right back out there. Now, this is actually the third interstellar object we've ever spotted. But trust me, 3I/Atlas is in a league of its own. Its arrival wasn't just unusual. It was just plain weird. Okay, so take a look at our other interstellar visitors. You've got Oumuamua and Borisov. They were pretty small, relatively speaking. But 3I/Atlas, it's a behemoth in comparison. We're talking nearly 6 kilometers wide. But its size isn't even the weirdest part. It's the way it showed up. Right. So the first two, they came at us from the direction our whole solar system is moving through the galaxy. You can kind of picture it like a head-on collision on a cosmic highway. But 3I/Atlas? Nope. It came smack in from the side. A perfect cosmic T-bone. And what makes that T-bone collision so strange is its alignment. Our solar system is basically a flat disk, right? Almost like a vinyl record. Well, 3I/Atlas came in at an angle of only 3 degrees off that disk. To put that in perspective, even Pluto's orbit is tilted by 17 degrees. I mean, for an object that could have come from literally any direction in space, hitting us almost perfectly side-on, that's a statistical long shot, to say the least. But believe it or not, its strange arrival was just the beginning of the mystery. As 3I/Atlas got closer to the sun, its behavior got even weirder. So, the first big head-scratcher was its coma. That fuzzy halo of gas and dust that gives a comet its classic look. Well, this one started forming when the object was still way out past Jupiter's orbit. That's over 5 times farther from the sun than we are. And it's usually just way too cold out there for a normal comet to start waking up. So why the early start? Turns out it's all about what it's made of. 3I/Atlas is basically a giant dry ice comet. Its coma is mostly frozen carbon dioxide, which turns from a solid straight to a gas, sublimates at much colder temperatures than regular old water ice. In fact, the ratio of CO2 to water was a whopping 8:1. That's the complete inverse of a typical comet you'd find hanging around our solar system. And then there's the way it reflects sunlight. This is pretty cool. Light's a wave, right? And normally, when it bounces off dust, it gets polarized, meaning it lines up in a predictable way. But the light coming off this coma showed something called extreme negative polarization, basically the exact opposite of what we expected. This is a huge clue that the dust itself is made of some really exotic stuff, maybe from a star system that's totally different from ours. But the weirdness just kept coming. As astronomers started looking at the different elements in its coma, they stumbled onto another puzzle. The mystery of the missing iron. Okay, so check this out. It's a really strange series of events. First, back in the summer, they detected nickel coming off the comet, but no iron. And that's super weird because those two metals are almost always found together, like cosmic buddies. Then, in September, bam! The comet suddenly burps out this huge cloud of water vapor. And only after that water burst did the iron finally start to show up, bringing the metal ratio back to what you'd expect. It's almost like the comet started acting more normal over time, but it did it in the strangest way possible. Oh, and as if all of that wasn't enough, when its tail first started to form, yeah, it was pointing the wrong way, towards the sun. Now, this was probably because the coma formed so far out that the solar wind just wasn't strong enough yet to push everything back. But still, a tail pointing at the sun, it just adds to the whole bizarre picture. So, with this huge pile of strange evidence, the big question is, what happens now? Where do we go from here? Well, for now, we wait. It's currently making its closest pass to the sun, and like we said, it's totally hidden from us. But in early December, it's going to pop back out from behind the sun's glare. Our best chance to get a good look will be around December 19th. And you can bet scientists will be glued to their telescopes watching to see how this super intense trip around the sun has changed it. And then, in March of 2026, we get one last chance to say goodbye. The Juno probe, which is already out there orbiting Jupiter, is going to be in the perfect spot to snap a final picture of 3I/Atlas. And that'll be it. Our last look before it heads back out into the interstellar darkness forever. You know, the story of 3I/Atlas is just this powerful reminder that our solar system isn't some isolated island. We're part of a vast, ancient, and incredibly weird galaxy. And it really makes you wonder, what other strange messengers from distant and maybe even long-dead stars are out there right now, heading our way?
Welcome to The Debate. So we're diving into 3I/Atlas today. This is the third interstellar object we've confirmed visiting our solar system. And honestly, it's rewritten the book on these kinds of visitors. It's just extreme in almost every way. Its speed, its size, and especially its chemical makeup. It really defies, well, pretty much everything we thought was typical for comets in our own neighborhood. Which brings us to our central question. What tells us more about these interstellar objects and where they come from? Is it the really specific path it took, its trajectory and galactic origin, or is it the frankly bizarre physical and chemical properties it showed? I'm going to argue that its orbital mechanics, its path and history are really the key here.
And I'm going to take the other side. While that path is definitely interesting, I think the composition, the chemistry, and how it behaved physically, those are the truly unprecedented markers. They scream foreign in a way that a general path through the galaxy doesn't quite capture. It gives us a much more specific fingerprint of where it must have formed.
Okay, so let me lay out my case. I really think the object's path, its kinematics, and specifically its alignment, these are the most compelling clues pointing to a distinct origin, maybe even a whole different population of objects we haven't really accounted for. First off, its interstellar status is undeniable. You look at the hyperbolic trajectory, the speed. It was clocked moving at a blistering 58 kilometers per second. And that was way out near Jupiter's orbit, around 4.5 AU. Clearly not bound to our sun. But the speed isn't even the wildest part. For me, the real shock is how it came in. Its path was only 3 degrees off the plane of the ecliptic, the flat disk where all our planets orbit. It's like a cosmic T-bone collision, as some have described it. Remember Oumuamua and Borisov? They came in at much steeper angles, sort of diagonally from above the plane.
Right. That 3-degree number is, statistically speaking, pretty startling. I'll give you that.
It's more than startling. It's statistically astounding, especially when you factor in the size of this thing. Atlas is huge, maybe up to 5.6 kilometers across. It dwarfs the previous interstellar visitors. Now put that together. This specific, almost flat entry path, combined with the theory that it might have originated way back in the galactic thick disk, that's a region with much older stars than ours, potentially making Atlas itself something like 7.6 billion years old. You start to see that maybe this trajectory isn't random. It suggests this ancient, massive piece of, galactic history got delivered right into our planetary plane. That gives us a really rare glimpse into how matter gets distributed over vast cosmic timescales.
Okay, I see the appeal of the grand cosmic journey argument, but I come at this from a different angle. Chemistry is destiny, or at least it dictates a much more specific birthplace. For me, the physical properties, how the comet behaved, what drove its activity, that tells us much more directly about the environment it formed in. Way more specific than just saying it's ancient. The first big clue was just how active it got, so early, while it was still way out beyond 5 AU, past Jupiter. You know, astronomers using instruments like TESS, they expected maybe a small brightness increase, like factor of 1.5 maybe. Instead, wham! The data showed its brightness shot up by a factor of 5. That means it was already forming a massive coma, shedding material. Now, typical comets we know, the water ice ones, they stay frozen solid out there. It's just too cold for water ice to turn to gas.
Right, and we know why it started so early. It wasn't water driving it, it was CO2, carbon dioxide.
Exactly. The early gas cloud, the coma, was overwhelmingly CO2. The ratio was something like 8 parts CO2 to just 1 part water vapor. That's completely backward compared to our typical solar system comets. It's more like dry ice sublimating. And that absolutely requires different conditions, different temperatures, where it originally formed. But the weirdness doesn't end there. Critically, 3I Atlas showed the most extreme negative light polarization ever seen. Polarization tells you how light scatters off the dust grains. Borisov, the previous interstellar comet, showed positive polarization, which is more typical. This extreme negative value, it means the structure of the dust grains themselves is fundamentally different. Maybe they're incredibly fluffy or highly porous, or shaped differently, like weird elongated aggregates. That's a direct physical property screaming that the basic building blocks are foreign to our local cosmic environment. It points straight to a very unique, very atypical nursery.
Look, I understand why you're focusing on the chemical complexity. That 8.1 CO2 ratio, the early activity, it's definitely fascinating stuff. But I still maintain those are consequences. They're effects caused by its specific materials meeting standard solar system conditions. The cause, the fundamental identifier, lies in its kinematics, that speed, 58 kilometers per second, and crucially, that 3-degree alignment. Those are parameters set by its incredibly long journey, its galactic history. These features strongly support the idea of an ancient thick disk origin, maybe double the age of Earth. And that tells us about a whole potential population of similar objects, how they're distributed, the huge galactic forces moving stuff around over billions of years. We could be looking at a 7.6 billion-year-old relic.
Understanding where something this massive, and it must be tough to survive that long in the galaxy, was stored for eons. That feels like a much bigger cosmological question than just the specific recipe of one comet. The path tells us about the population. The chemistry describes an individual, however strange.
I'm sorry, but I just don't buy that the chemistry is secondary here. A generalized path gives us probabilities, maybe. But unique chemistry? That's a direct signature of specific processes. And the chemical profile wasn't just about causing early activity. It showed really bizarre material transitions during its flyby, things that just scream unique processing history. Think about that sudden, massive burst of water vapor when it got closer, near Mars's orbit around 1.5 absolute unit. We've never seen anything quite like that sudden turn-on. And even earlier, the detection of nickel in its coma, without its usual partner, iron. Nickel and iron, they're usually found together, right? They're made in the same stellar processes. They condense together in dusty disks where planets form. But early on, Atlas showed nickel, but was weirdly deficient in iron. The iron only really showed up much later. That separation isn't just a difference in starting materials. It strongly suggests some kind of intense, very specific processing, maybe weird heating inside the comet, selective vaporization, something unique to its home system that separated these elements. That kind of specific processing history tells you much more about its unique birthplace than just saying it's generally ancient. And about that thick disk idea, it's compelling, sure, an ancient reservoir, but what about that extreme negative polarization? Have you really considered how profound that is structurally?
Like I said, polarization probes the actual shape and texture of the dust grains. An extreme negative value isn't just a little different. It implies the fundamental building blocks of Atlas are structurally unlike anything we typically find in our asteroid belt or the Kuiper belt. They're probably these really porous, complex, maybe fractal aggregates that formed under very different conditions, maybe low density, maybe high radiation in its original star system. That's direct physical evidence challenging our basic models of how dust even clumps together. Its alignment? Yeah, it's statistically weird, I grant you. But couldn't it just be, a random geometric fluke? Space is big and three-dimensional. Billions of years of getting kicked around, weird alignments happen. Building a whole theory about galactic populations on one geometric coincidence feels a bit shaky to me.
I find that skepticism a bit unwarranted, actually. Let me frame the statistics differently. If it were purely random, why would an object this massive, again, up to 5.6 kilometers, way bigger than Oumuamua or Borisov, coming from the general direction of the galactic core, happen to hit our thin planetary disk almost dead on? If it really did come from the thick disk, its sheer size implies it survived the rough and tumble environment of the inner galaxy for potentially billions of years. So it's not just the angle, it's the angle plus the mass plus the implied origin. The whole package, hyperbolic path, huge size, near-perfect alignment suggests its entry wasn't random relative to our system's plane. It gives us this incredibly rare chance to study stuff delivered via this specific, nearly flat vector. Maybe that tells us something about the stability or instability of that thick disk. How do massive, ancient things get nudged out and end up aligned like this? Maybe galactic bars or spiral arms play a role we hadn't considered for this kind of delivery. And let's swing back to the observable stuff, the behavior. You pointed to the early CO2 activity as proof of unique chemistry. But I see that chemistry as just the engine that made it visible and behave weirdly far out. Remember the initial tail. It pointed towards the sun briefly before flipping to a normal away from the sun tail later on. That's a direct result of the CO2 sublimating so fiercely so far out past 5 AU, where the solar wind was still too weak to push the gas and dust back properly. So that weird early tail tells us more about its high speed and the physics of interacting with a weak solar wind way out there, rather than fundamentally about its birthplace. The object's true identity, its significance, is rooted in its ancient, high-velocity, precisely aimed journey, not just the chemical trick that lit it up early.
I'm still not quite convinced by that reasoning, because detecting any metal sublimating, specifically nickel, way out beyond Mars, where it's incredibly cold, that needs a serious, sustained energy source beyond just CO2 ice turning to gas. Okay, maybe the CO2 gas rushing off could drag some nickel atoms along, fine. But that initial, persistent lack of iron, that remains a profound chemical puzzle. We know these metals formed together, condensed together, so their physical separation early on having the nickel without the iron suggests one of two really strange things. Either Atlas formed somewhere that just didn't have much iron but was oddly rich in nickel, which is really weird from a stellar nucleosynthesis perspective, or it went through some kind of intense internal heating that selectively boiled off or chemically locked up the iron compounds, leaving the nickel more accessible until later.
Either way, that level of unique processing, be it thermal or chemical, points directly to a planetary formation environment drastically different from our own solar nebula. And that information about the sheer diversity of how other star systems work feels far more fundamental than the geometric coincidence of its arrival angle.
Well, we certainly agree that Atlas is a phenomenal object that shatters a lot of assumptions. To wrap up my side, I believe the trajectory, the sheer size, and that striking 3-degree alignment strongly point to 3I Atlas being a representative of a distinct ancient population, likely from the galactic thick disk. These kinematic clues give us a unique window into galactic dynamics, the structural history of the Milky Way, and how massive chunks of matter get stored and moved over cosmic time. It's insight into the galaxy's very infrastructure.
And while I concede its path raises fascinating statistical questions, I have to stand by the idea that the extreme physical and chemical anomalies are the real story. That 8-to-1 CO2 dominance, the direct evidence from polarization for unique dust structures formed at low temperatures, and those bizarre initial metal ratios,
This is direct physical proof that Atlas formed in a protoplanetary environment wildly different from ours. This chemical fingerprint fundamentally challenges our models of comet formation and directly illustrates the incredible diversity and complexity possible in other star systems, maybe in ways we haven't even imagined yet.
It definitely forces us to rethink what normal even means, both for how things move through the galaxy and what they're made of. It seems the universe is full of these massive, ancient wonders.
Strange processing that interstellar material undergoes out there in the void. It really shows that the only constant might just be variation itself.